Hello, welcome to this little video on simulating physically accurate depth of field. We're going to talk about some lens physics terminology, enough to understand depth of field behavior, what variables can affect depth of field behavior in a lens, and yeah, we're going to talk about how to simulate accurate depth of field in a compositing context. So to start off, depth of field is a hugely important part of cinematography. It's used, in all forms of cinematography, and it's hugely important. It's a vital part of how a photographic image looks. It's used as a way to focus attention of the viewer, and it's generally awesome looking and yeah, very important to simulate correctly when you're trying to create a photoreal composite. So these are just some images that I've shot over the years. And yeah, so you can see that there is bokeh that's formed when an image is out of focus, and in the range that the image is in focus, it's not really like here nor there. Like, it's not a long range. It's basically a triangle. And to explain that more clearly, I have a diagram here. So this diagram represents a camera's field of view. So you have a camera over here, a lens, which has a field of view like this triangle, and that's called the camera frustum. The frustum is basically the edge of the field of view of the camera, and the farther away you are from the camera, the bigger that triangle becomes. So this is a representation of distance, and a lens has a focus point, which you basically adjust to set the distance from camera that the focus plane is. And so the screen line here represents that focus plane. And then you have what's called a circle of confusion. Now, a circle of confusion might sound confusing, but it's actually pretty simple. It's the basically the size of a point of light that is resolved by a lens. So when we're looking at these images here, maybe this is a good example. So these bokeh that are forming are a bright point of light that's far away from camera that's out of focus. So it's called a bokeh, and it's also called a circle of confusion. So you have a circle of confusion size. And so what is depth of field? So that's a good question since we're talking about it. Depth of field is basically the range of acceptable focus from near to far. That is basically a circle of confusion size that's smaller than the acceptable circle of confusion. So the acceptable circle of confusion, I have all of these written out here. The acceptable circle of confusion is the maximum blur spot size that will appear to be acceptably sharp. So if you take a photograph, how sharp is acceptably sharp? Well, that depends on a number of variables. It can depend on the sensor size, the resolving power of the lens, the viewer's vision and how good it is, how big the screen is that the person is viewing and how far away it's being viewed from. All of these variables can determine the maximum acceptable circle of confusion size. And for our purposes, we can just think of a circle of confusion as a bokeh size. Maximum circle of confusion size is more relevant for print photography and stuff like that. In compositing, usually we are concerned with matching a plate and creating a photoreal composite. So the important concept here is how circle of confusion size changes over depth. And so if you see this triangle here, this represents the circle of confusion size changing. So at the focus plane, is the only place that there will be a circle of confusion size of 0. Everywhere else over the distance that the camera is looking at, the circle of confusion size is going to be greater than 0. But in this diagram, between this point and this point, these points are acceptably sharp. And then in front of that and behind that, the circle of confusion size is greater, and it forms what is perceptibly apparent as a bokeh shape. Cool. So just really quickly, another important concept, which is pretty relevant and sort of is a good jumping off point to explain the rest of this. Hyperfocal distance is the minimum focus distance such that the range from half of the hyperfocal distance to infinity will be acceptably sharp. So basically, and it depends on the focal length, the lens f-stop, the film back size, and the focus distance. And it's basically a way of optimizing your range of focus. So if you put the focus plane further and further away from the camera, eventually the circle of confusion size at infinity is going to be less than the acceptable circle of confusion size, and it'll appear sharp. But there's a trick if you focus a little bit closer than that, so that the hyperfocal distance means that from half of the distance from the camera to infinity is acceptably sharp. And it's basically like if you focus at infinity with the lens, you're actually losing depth of field and making foreground objects less sharp than they could be. So if you focus just enough forward so that infinity is still acceptably sharp, you get a maximum range of focus. It's usually used and calculated for landscape photography by nerds like me, and it can help get you more depth of field, basically. So it's interesting, the variables here. So focal length affects depth of field and depth of field fall off behavior. So hyperfocal distance will change with the focal length, the f-stop, the film back size, and the focus distance. In simple terms, the wider the lens, the nearer to camera the hyperfocal distance is going to be. So with a long lens, like a telephoto lens, usually you'll notice that the depth of field, you have to focus further from the camera in order to be able to focus to infinity. So I have some helpful diagrams here to help explain this from this excellent article, which you should check out and read. So basically, here's a graph of depth of field versus aperture. So same as the previous diagram, we have the camera here, and we have a representation of the depth of field. So a short depth of field is a shallow depth of field, and the longer it gets, the wider the depth of field is going to be. So in this diagram, the focal length is constant, so it's an 85 millimeter lens, and then we're varying the aperture, so f2.8, f8, f22, to stop down the lens and let in less light. So you can see that the wider the aperture, the shallower the depth of field is, which makes sense. Like if you've ever taken photographs with a manual lens, you know that the wider you are with the aperture, the more light is going to come into the camera, and the shallower your depth of field is going to be. So this should be pretty straightforward. So here's a representation of depth of field versus focus distance. So you can see here that the focal length is constant, the aperture is constant, so it's an f8, and then we have the focus distance set differently. So when the focus distance is close, the depth of field is shallower. And if you've ever seen a macro photograph of like a bug or a coin or something like that, you sort of see this behavior pretty clearly. Like macro photographs have very shallow depth of field. That's because the focus distance is very close. So the further away the focus distance gets, the wider the apparent depth of field is. And yeah, so that should be pretty straightforward as well. And then here we have a representation of depth of field versus focal length. So here we have different focal lengths of lens, so a 50, an 85, and a 200. so going from medium to very telephoto. And the aperture is constant, so we have an f8 aperture, and the depth of field is represented here. So basically, the wider the lens, the longer your depth of field is going to be, and the more telephoto your lens, the shallower it's going to be. Cool. So all of those variables are things you should sort of intuitively understand and know when trying to match the defocus in a plate in order to do a photoreal composite. It's pretty important to sort of get a feel for how this is and how this behaves and sort of try to match it as best you can. Cool. So I'm going to stop there and switch gears for a second to sort of how you simulate depth of field in Nuke. So the simplest way to do this would just be, well, actually, the simplest way would probably just be to blur your image. So if you blur your image with a blur node, you can kind of see what happens. Everything just becomes smeary. And if you look at these photographs, things are not blurry. Like there's sort of sharp edges that form on the edges of highlights, and there's complexity here. Like the bokeh shapes that are formed have sharp highlights on the edge. There's aberrations. There's sharp edges of the bokeh where there are highlights in the background. This is a good example. This leaf has water droplets on it that are bright, and there's sort of this very optical, painterly quality to the edges of the highlights. And a blur does not simulate this at all. And there's, aberrations that can form, sort of mirror effects, like little spots in the center of the bokeh. Bokeh is not round. Like some lenses form bokeh that are actually like sort of warped or triangular. Different lenses have different number of sides to the bokeh. Like if there's a 5-sided aperture, it forms a pentagon shape. And there's complex behavior that happens when an in-focus thing goes over a bokeh. Like here you can see the edge is sharp here, but there's a bokeh sort of behind it. So the layering is very complex. Optics is, very complicated and awesome looking and difficult to simulate with computer graphics. But if you sort of take the real world as a jumping off point and like see all the cool things that happen, you'll be in a better spot than trying to simulate depth of field with a blur. So yeah, and yeah, look at that. It's crazy. It's like a rainbow. It's awesome. Anyway, so a blur is something you don't want to do. Like it's good for defocusing mattes or doing, simple stuff where you just need to soften something. But to simulate optical convolution, you need something more complicated. So we have a defocus node, which is basically a poor man's convolve. Convolution is the term used for what a lens does to a point of light. So if we defocus our image, you'll see something a little different starts to happen. We get sort of a hint of the line behavior that we were seeing in some of the photographs, where the bright spots and the dark spots and the lines of contrast sort of form lines in the bokeh. But it's basically a cheap but fast solution for doing that. So if you're doing something simple and you don't need complexity or something that looks awesome, you can use a defocus. It works pretty well for a lot of stuff. But what you want to use for simulating defocus is actually something like a ZDefocus, which I'm sure many of you have used. But so today I'm going to talk about sort of how the ZDefocus works in terms of the concept behind it, and then go on to show you some other stuff. So here I just have a checkerboard, very simple. There's an alpha channel and nothing else, and I'm making a ramp which goes from 0 in the left corner to a value of 1 in the right corner. So I'm going to use this as a z-depth channel, and a z-depth channel is basically a representation of the distance from camera of each pixel. So if we look here, we have our RGB and we have our depth, and it goes from 0 to 1, just like our ramp. And we have a ZDefocus. And in the ZDefocus node, I have the focus plane set to 0.5. So if you imagine here, like if this is 0.5 units from camera, I'm setting the focus plane to there, basically. And you can see that we get a basically a defocused image that's varying in the amount of defocus from camera to a value of 1 unit from camera. So with the ZDefocus node, you have a few controls, and there's a helpful little focal plane setup overlay. So you can see red is in front of the focus plane, blue is behind the focus plane, and green is the focus plane, which you can barely see here. If you increase the depth of field, it's basically a way of increasing the range that is in focus. So if we set this back to result, we should see that all of this is now in focus. And then we have a size and a maximum. So a maximum is basically a clamp on the maximum blur that can happen. So if you set it to 100, should see that this side close to camera actually gets a lot more blurred because it's getting very close to the camera's optical center, which means it's very, very defocused. So generally speaking, if you set this a bit higher than your size, you should be good. And yeah, if we bring the focus plane back and set our depth of field back to 0, because depth of field, like in a physically accurate sense, should be 0, because the focus plane is the only slice through space which will actually be sharp. So it's good to keep this at 0. But yeah, the problem with the ZDefocus is that the whole algorithm is sort of a hack, because it's not based on anything that's physically accurate. You're just sort of adjusting these parameters to get a result that looks correct. So it's super useful for a ton of stuff and works really well for what it does. But if you're simulating depth of field in a plate that was shot with a camera with a known focal length value, a known focus distance, and like a known film back size, you can use that information to simulate the depth of field that's happening in the plate instead of using the ZDefocus, which sort of gives you a approximation of the actual behavior of a lens in the real world. So how do you do that? Well, I spent like a weekend trying to remember how to do math and breaking apart this depth of field equation. So this is a screen grab from Wolfram Alpha, and it's the equation used to calculate the depth of field in an image. So this is actually calculating the depth of field for a photographic lens, and the variables you plug into it is the focal length, the f-stop aperture value, the focus distance, the circle of confusion size, and it actually calculates the near limit of the depth of field and the far limit of the depth of field. But what you can do is you can actually rearrange this equation to calculate the circle of confusion size at a given distance, given the focal length, the f-stop, and the focus distance, which if you have a depth channel, it allows you to calculate the circle of confusion size at an arbitrary pixel. So to do that, you basically have to do some math to calculate a new z-depth representation of the circle of confusion size, and then set the math to direct in your ZDefocus. So yeah, before I go into that, I have some more example images and a cool little visualization tool. So I shot some pictures in the park outside my house, just sort of more examples of depth of field. Look at that bokeh, it's cool. So, and these were shot with a 50mm lens on a Canon 60D, which is a crop sensor. So it's about an 85mm lens equivalent. And when you focus close, you can see the depth of field is pretty shallow. Like it ramps off from maybe the focus distance of here all the way towards infinity that we can see. And the further away we focus, like now the focus distance is here, nearer to camera is in focus or out of focus, and the further away we get, the more defocused the image is. And if we focus closer towards infinity, it's not completely at infinity, but we can see that the depth of field behavior changes, so that this is in focus, this is still a little out of focus, and this is a little out of focus. So here's another example. So if we focus close, everything is sort of out of focus back here. And this is a good example where you can kind of see what happens over distance. Look at that flare. That's cool. So back here, this is maybe about the same bokeh size as what would be infinitely far away. And where we're close, things are in focus. And when we focus maybe halfway through our scene, the stuff infinitely far away sort of gets a bit more in focus, but it's still out of focus, and this is still out of focus. And then when we focus infinitely far away, there's like some lens aberration and fringing and stuff that's happening, but it's pretty in focus here. And then closer to camera, it's out of focus. So that's sort of the behavior of a longer lens. And this is even more extreme. So remember the diagram showing you depth of field versus focus distance and how shallow the near focus distance is. This is a good example of that. So when we're near focus distance, look at how crazy shallow that is. Like we have a tiny thin slice that's in focus right on this weird piece of bark, and then far away, the infinity circle of confusion size is huge. Like it's way bigger than the previous example we saw here, just because we're focused closer. And when we focus in a medium way, the stuff that's closer is way more out of focus, and the stuff that is about as far away as this image is about the same focus size. And then when we focus infinitely far away, the near stuff gets even more focused. So sorry for banging this into your head, but it's pretty important to understand. And then here's another example, just two images sort of showing what happens when you focus closer and then farther away. Same behavior. Cool. So that's with an 85mm lens. When you have a wider lens, you can kind of see what happens. Like suddenly we don't really have that focus plane visible, because remember what happens when you have a wide lens. In this one, the focus distance, the depth of field range is much larger, and the hyperfocal distance is much closer to camera. So when you focus even a little bit from camera, suddenly infinity is in focus already. So this is like a super important characteristic of wider angle lenses. Cool. So I did this crazy thing and made a LiDAR scan of the scene that you see in this photograph. So using PhotoScan and some MeshLab, Voodoo, and stuff, and this isn't very well aligned at all, so yeah, it's sort of rough, but you get the idea. Just want to use it to sort of show you the behavior. So so you can see the same poles here that were used in the photograph, and the sidewalk and the side of the building, and a roughly match moved camera here. So I wrote this other gizmo called Defocused, which basically calculates a camera. There's a bug here where it won't deselect. Okay, so it basically calculates the near and far depth of field and the focus plane. Given a focus distance and the characteristics of the camera, the lens geometry. So if you open the camera and adjust the focus distance and f-stop, you can sort of get a visual sense for how these things are changing. So with this wide lens, and I apologize, I don't think the depth unit is correct here either. This is 20 units from camera, so it's probably like somewhere between feet and meters. Anyway, you get the sense for how it behaves at least. So if you focus at 2 units from camera, which is super close to camera, the far depth of field is already almost 20 units away, and the further we go, so this is at 2.3 units from camera, and suddenly the far depth of field is almost at the wall. And the moment we go like even a reasonable distance from camera, infinity's in focus. So that's a very common characteristic of wide-angle lenses. And similarly, if you open the f-stop, the depth of field is going to get shallower. So if we stop down to something impossible like f.4, the depth of field is going to be shallower. But the moment we stop back to something physically accurate like f2.8, everything is going to be in focus. Cool. So if we switch to the 50mm lens, our field of view is suddenly a lot less. Like we're seeing a triangle that's like this instead. And you'll see what happens if we focus to something close. Our depth of field is super shallow. And this is with an f-stop of 8, so with the same f-stop of 4, it's even shallower. And the further away we focus, like see how you can sort of see the range of focus? Like this is out of focus already, this is out of focus, and this is in focus. So it's the same behavior we're seeing in this example, where when you focus sort of far away, you get something that's in focus and you see the depth of field fall off visually in the image. Cool. So that's, important. Cool. So how do depth channels work? Here we have a terrifying image that's sort of stretched and weird. It's basically just like projecting my crappy match move of this image onto this geometry and rendering it out through the scanline render. I think I actually was like moving this camera to test it, but yeah, whatever. Anyway, I just want to show you Z-depth render. So if we look at the depth channel, you'll see that we have a Z-depth render. And you can see it's kind of weird, like it's a red image, and the further away from camera it gets, the smaller it gets. So the farthest away we see is, so once this calculates, I have this set to like 5K to match the photograph, so it's a little slow. So it's like 0.02. Okay, so that's a little different than what we were seeing up here, because this is basically a ramp going from 0 to 1, right? And we're defocusing here, and this was behaving such that this is closer to camera and this is further away. Well, it turns out it depends on the math that you specify. So if you mouse over this, you can see that if math is set to depth, it'll calculate it so that Z is distance in front of camera. So basically, the further away from camera the depth gets, the bigger the value gets. And then there's another option called 1 over Z. Wait, what is it? Far equals 0. So so that's 1 over distance, right? Which is how Nuke scanline render calculates depth information. So if we're working with depth from any common render engine like V-Ray, Arnold, RenderMan, most of them will render Z-depth as absolute world units distance from camera. So the further away the depth gets from your camera, the bigger it gets. So if you're rendering stuff out of your scanline render and you want to match defocus with a CG render, a lot of times you'll have to reverse the scanline render depth to be distance from camera instead. So it's super simple. You basically just say 1 over Z on your depth, and that'll reverse your depth to be basically distance from camera instead. So here we have a value of 6, and here we have a value of 17, and here the farthest away is a value of about 44. So that's cool. And then we can use that to sort of simulate depth of field in ZDefocus and use scanline renders and CG and have it all defocused by the same thing and match. Cool. So I was talking earlier about me spacing out on a weekend and nerding out and trying to figure out math again. So basically, I built a tool called OpticalZDefocus. Oh, by the way, if you haven't read the depth of field article in Wikipedia, you should, because it's super helpful and there's a ton of great info in here. So check that out. And then the OpticalZDefocus tool that I wrote just got put up on Wikipedia, so it's there for you to check out and use if you like. So the OpticalZDefocus tool is basically a ZDefocus that calculates physically accurate depth of field based on lens geometry. So if you have a checkerboard and a ramp, and this time I'm going to multiply it up by 100 so that we're not dealing with something that's, 1 decimeter from camera, like super close. And then we copy that into our depth.z. So here we have it going up to 100. And then we plug in the OpticalZDefocus and look at its output. So the focus distance here is set to 50, which should be halfway. And the focal length is set to 30, and the f-stop is 4, and our h-aperture is 24. And there's a cool thing you can do where you can select a camera, like say we want to grab the 50mm camera, and we can get the values from it. Just select it and hit the button, and it grabs the focal length and h-aperture automatically. So this actually simulates the physically correct depth of field behavior based on the lens geometry and based on the distance from camera. And it's super important to know what depth unit your depth is rendered as. Different pipelines have different depth units. Some are decimeters, some are feet. But if you choose it here, you can set that. And then the depth.z is the depth channel we're using. And then also super important, if you're working with CG that has any transparency, you want to unpremult your depth channel. Otherwise, you're going to get edges that are premultiplied. The scanline render doesn't do that, but a lot of render engines do. So just to show you, if we well, this is actually doing math to fix it. Basically, if we see our depth here, so, and yeah, let me just do a simple expression to reverse it so you can see. So depth is 1 over z. Okay, well, this is kind of a terrible example, but the concept still stands. So this is going to be infinity because it's 1 divided by 0, which is infinity. It's actually not, it's a divide by 0 error, but Nuke outputs infinity. And this pixel is 43 units from camera, and then this pixel is 95 units from camera. That doesn't make much sense. So yeah, you have to unpremult your depth so that that pixel is actually calculated correctly. Otherwise, you're going to get giant bokeh on the edges of your defocus, and shit's going to get weird. So make sure to do that. Cool. So here we can enter our values. So yeah, you basically animate the focus distance or set it, and you want to make it something that's plausible in your scene. Like sort of look at your depth render, look at your plate, and try to figure out where the focus plane should be. Once you set that, you can adjust the f-stop to set the bokeh size to match your plate. So if it's an f8, this will be more in focus, and you sort of just adjust this to match your plate, and then animate your focus distance. And if you need to tweak it, it should get pretty close when you first set it up, if the depth unit is correct and the focus distance is correct. So yeah, the only thing you should really need to animate is focus distance, but sometimes you need to hack things, so you can always cheat the focal length to get it to be the right behavior and stuff like that. Anyway, so And to show you why it's important to get your depth unit correct, if you set this to like millimeters, you'll see what happens. Like everything just explodes because it becomes suddenly like very close to camera. So yeah, that ain't right. Cool. So there's a cool thing you can do where you can say show COC, and this is actually a visualization of the circle of confusion size over distance. So if we look at this here, you can see these pixel values are 0 where the focus plane is and get bigger the further away you go. And if you want, we could actually plug it into here and set this to be, what was it, like 20? So you can kind of see the visualization of the depth of our fake LiDAR scan. So here's our focus distance, and here's our foreground, which is a defocus size of 43. Here's our background, which is a defocus size of 10. If we look at the RGB output again, oops, we'll see that it's actually defocusing our image. Our 5K image, sorry. And then there's also a sort of a utility mode called constant defocus. If you turn this on, it'll basically defocus the whole image the same without calculating depth of field fall off, which is a lot faster. And a lot of times in a lot of shots, like, you don't need depth of field fall off. So if you don't need it, you can just set this on and use it. Cool. So here's another CG example. Apologies for the crappy CG. I just built this in a few minutes and rendered it out just to have an example. So we have depth, and we can see that it's encoded in distance from camera. So the further away we get, the bigger the values get. And the scene is huge, like it's 1500 units to the farthest thing we can see. And far away is very far away. So same thing here. If we set our depth unit to meters, I think it is, and our focus to, let's say 800, we can see that that's our depth of field, which makes sense because we have a 50mm lens and we're focusing pretty far away. If we set it to be a 200mm lens though, 500, yeah, it's not really changing much. Maybe if we focus closer. Oh yeah, another feature is if you move the sample Z, it's actually changing the sample position here, and you can click sample Z to grab that value at that pixel from the channel you have specified. So it's a useful shortcut. Cool. So I'm going to open our f-stop a bit more, say f2.8. Maybe our depth unit isn't meters, maybe it's decimeters. Yeah, so if we do that, everything changes to be crazy. And yeah, we can change our focus distance. And the cool thing is that, this is all working as an actual lens would, and it's a lot more physically accurate. So a limitation of convolution is that we are sort of just convolving stuff into a round shape. The ZDefocus has options for changing that, like you can change the filter type to a disc or a bladed representation, or actually a filter input, and you can actually plug an image in here. So that's a pretty useful strategy for simulating bokeh in plates. Because, if you look at images, like there's crazy stuff that happens, like pentagons, bright and dark outlines, shapes in the middle, weird stuff, random dots. So you can actually simulate that if you use the filter input. So I have one of these images, just contrasting it up a bit and running it through an OpticalZDefocus set to constant mode, and I have the filter input plugged in. So inside of here, there's a default filter which just looks like this, and then if you plug it in, you can actually use an image, And then in the ZDefocus that's in here, we're just saying filter type is image and use input channels in case there's any aberration. So in here, you can actually see now that the bokeh shapes that are forming, like this is a little overbright, are actually the shape and texture of the image that we have plugged in. And so it's a super useful strategy to sort of look at your plates and find a bokeh and steal it and use it as a filter shape. It can really increase photorealism and help out a lot. And yeah, it's pretty cool. Another important concept to note is that a bokeh shape only forms when there's a point of light that's brighter than its surroundings. You know, if you defocus a constant, it's not going to have any bokeh. So that's important to know when simulating bokeh, because sometimes, you know, you'll have a plate that has clipped values like this. Like if you gain down, there's no overbrights. And overbrights are super important to forming bokeh. So if we plug our defocus directly into that, we'll see everything just sort of gets blobby up here. Like there's no bright pings from the sun. So you can kind of simulate this if you run some noise through it and grade up your plate to add some sparkles. But just to demonstrate what happens if you, just gonna remove the strokes I made here. If you make a rotopaint node and plug it into a grade as a mask with a gain of like 120, like something crazy, and you start painting some stuff. I'll do one over here in the dark. Hello. Yep, so the more you paint, there we go. Not sure what's happening there. So the more you paint, the more of a bright bokeh you'll get. Something weird's going on with my cache. Oh, there we go. All right. So the if you paint a bright spot, it's going to form a bokeh shape. All right. Fuck you. If we paint a bright spot, oh, seriously? If we paint a bright spot, it's gonna form a bokeh shape. Aha! So yeah, it's if you're simulating bokeh, it's just good to know. Like if you sometimes if you want to just put some bokeh back in a defocus background, you can just you know, grade up your specular or add some pings and just track it in and get bokeh that way. So it's useful to know. That's pretty much it. I hope this was useful, and I don't think I forgot anything. Yeah. Hope it helps, and happy defocusing.